Let's answer question 19 through code. Here are the necessary imports that we'll need to use, and I'll load my free IBM Q account using the python.env package, so that way I don't have to specify my API key in this string, and that way I can keep it secret. And question 19 says, what would be the fidelity results for these two operators which differ only by global phase? So we have an operator A, and it's the X gate. An operator B, that's also the X gate with a global phase factor of e to the I over 2. So first I want to gain some intuition behind what would happen if I use these in a real quantum circuit on real hardware. Quantum mechanics tells us that the probability of measuring the same result with a global phase operator and non-global phase operator, when they differ only by a global phase, there should be no difference, and you shouldn't be able to notice the difference in measured results. But I like to test those assumptions and not rely on them. So we'll create two quantum circuits representing the NOT gate on state 0, and see if we get the state 1 in both of them and what the differences are between these two quantum circuits. One with the global phase, one without. So for a custom gate or a instruction or operator, you have to use the append function. There's no H or CX property function for the quantum circuit like there is for the Hadamard and CNOT. And so we use the append function to give it the custom operator, and then a list of qubits that we want the operator or the gate to be surrounded around. So that we want it to work on qubit 0, and we want to measure all of them so that we can get classical results from it. If we don't measure, then we can't see any actual meaningful results from our quantum program executing. And let's do this on the real hardware to see if the real hardware has any interesting noise, or maybe the global phase does affect it and we just didn't know. So we want to make this fast though, so we can call the least busy function that will give us the least busy backend given the list of backends. And we can filter the list of backends given a custom function with one variable. And so that variable will be a backend. We can see if its configuration has enough qubits for our quantum circuits, and make sure it's not a simulator, and make sure that it's currently operating. So that'll give us the least busy function, backend, and then we can give it an array, the execute function for that backend, an array of quantum circuits so that we don't have to run them in different jobs. And with 1024 shots should be enough to sample the probability space and to understand what the mean values look like. And so that will run and send the job to the corresponding backend. And we might be waiting here an hour if it was a busy one. Because it's least busy, hopefully it's less than 1 minute. But we can run other code before we actually get the result. And so then once we get the result, it will wait here until the result's done. And when that result's done, we can get given the name of these quantum circuits, the counts related to that quantum circuit result and the job. So here the results are back, and we see that they are relatively the same, not too far apart. Let's plot them together on the same histogram to look at the differences. We can do that with an array of counts, and then we can specify on the legend what counts correspond to which operations that we did. And sorting by descending allows us to see the highest keys first to 0. And so here we see that the global phase did a little bit worse than the X gate without any global phase. But I've run this other times and got better results with the global phase operator than without, which is very interesting. And so since the results will differ from run to run, we see that it actually doesn't affect the measured results significantly. Like global phase doesn't cause a significant decrease in accuracy. which is what we expected. So the fidelity should be 1 of these operators, but which fidelities are accurate here? The process fidelity can be computed with the process fidelity function. The target, we can specify a unitary that we want to match to. And so here we say operator A is our target. We want to compare it to the global phase operator. And there we see a 1 for the process fidelity. So they act the same in process. What's actually going on here, we can compute that. So the Qiskit documentation says that the fidelity of a process between epsilon and a unitary u is equal to the trace of a product between its superoperators. So that's what the S means, is it's a superoperator corresponding to the matrix u and epsilon. So we can do that with the superop function, giving it our operators, and that will give us the corresponding superoperator for that operator. The D is the dimension, and since the row and column have the same dimension because it's square, we can just get one of them, and it should give us 2 in this case for operator A. And interestingly enough, even though the operator B has this global phase complex number factor for the 0, 1, 1, 0 part of its elements, we don't see any global phase in its corresponding superoperator. And it's the same as superoperator for A. They're the same. So this trace, this product, should equal to the identity. And the trace of the identity is equal to its dimension. So that would be a 4 by 4. So we get a 4 on top. And D squared is also 4. Computing that here with this code shows us we get a 1, just like expected. Average gate fidelity can be computed similarly with the target. And we could do the math here using our fidelity of the process that we got from the previous execution to see it's also a 1. So what is the state fidelity? We get an error. Why is that? That's because the inputs are not quantum states. In order for state fidelity to be accurate, to even account or have a definition, they need to be on 2 quantum states. And these operators are not quantum states because the Pauli matrices, like the X gate, Z gate, Y gate, are not valid quantum states. A density matrix is a valid density matrix if the trace of its square is equal to 1 or less. And since the trace of the Pauli matrices, its square is greater than 1, because it's going to equal the identity, then they are not valid density matrices. And neither are the valid state vectors, which is required for a quantum state. To check that that's the case, we can see if a density matrix for operator B is valid. And here we see it's not. So there is no corresponding state fidelity, and thus answer C is the right answer, and not D.